Okay, two things. First of all, here is sort of proof that, in fact, this is an identity, which means for all values of x, the left side is always equal to the right side. These two graphs are identical. So I'm kind of convinced that we should be able to prove that the left side always equals the right side. When you're proving an identity, you usually pick the more complicated side and make it look like the other side. In this case, these two sides are both about the same complexity, so I chose to work on the left side and make it look like the right. Is this the only way to do this problem? I have no idea. But I did originally try multiplying top and bottom of this first identity by tangent x minus sine of x, but it kind of didn't lead me anywhere. So I said, you know what? When in doubt, punt. The reason I'm punting is because when I was in high school, my trig teacher was also the football coach, and he used to say, when in doubt, punt, which in trigonometric terms meant turn everything to sines and cosines. So that's what I did here. I replaced this tangent of x with sine x over cosine of x, and this tangent of x with sine x over cosine x. And then I multiplied top and bottom of the big fraction by the cosine of x so that I didn't have a complex fraction anymore. So that led to these canceling out in the numerator, giving me sine squared. And in the denominator, when I take cosine of x times this term, the cosines canceled out, and I get just the sine of x and plus sine x cosine x. And then I noticed, hey, everything's divisible by sine of x. I factored out the sine of x from the denominator, canceled out one of these sines of x's, and I'm left with this. And then I said to myself, well, that's not looking like the right side very much, but I noticed that if I multiply by the conjugate of the denominator, that I'll get a difference of squares. 1 minus cosine squared is sine squared. And I don't have two terms in the denominator anymore. That's what led me to that thinking. And in the numerator, I still have sine of x times 1 minus cosine of x. In the denominator, 1 minus cosine squared replaced with sine squared. And then one of these sine squareds cancel out, and I've got 1 minus cosine over sine. I seem to be going nowhere. But then I took a look at what I'm trying to end up with and noticed that what I'm missing in the denominator is a tangent of x. So I multiplied top and bottom by tangent of x, and my denominators match, and I cross my fingers, do the numerators match. So tangent of x distributed over this binomial in the numerator gives me this. My denominator matches now, and what I did was convert this tangent of x to sine x over cosine x again. And these guys cancel out. I used the commutative property for multiplication to interchange these two. And what do you know? They matched. QED, that which was to be proved. This side is equal to that side. Okay. Are there other ways to do it? Probably. There might be an easier way, but that's the one that I stumbled upon first. There you go. Hope that helped. If you have any questions, post a comment.